Hello everyone, Programmers Paradise would like to welcome you to today's webinar sponsored by Intel and Microsoft. Today's topic will be Go Parallelism, the ease the on-ramp for C++ Windows development. We'll take a look at today's agenda real quick. We're going to go into who we are, and then we also have with us today Dana Groff, who is a Senior Program Manager with Microsoft, and Shobhan Jha, who is a Product Marketing Manager from Intel. After they do their presentation, we'll get into questions and answers and then a summary. So who we are. Programmers Paradise is a Microsoft Gold certified partner. We're a leading e-seller of developer and infrastructure tools. You can see all of our offerings at www.programmers.com. You can also view our ALM Worldview ecosystem, and you can find all our Microsoft and Intel products listed on the site. Here's our ALM Worldview, and again, you can check this out on our website. We provide industry-leading tools for your end-to-end development needs. And you can also see Intel's HPC and multi-core development tools, which are available at www.programmers.com/Intel. So now, first off, I'd like to introduce Shobhan Jha, who is, again, the Product Marketing Manager over at Intel. So go ahead, Shobhan, and take it away.
Okay, great. Thank you very much. We're going to start the presentation here. The first slide.
Hold on, Shobhan. I'll fix it right now for you.
Okay, thank you. Okay, great. Sorry for the little quick mix-up there, but today we're going to talk about easing the on-ramp to C++ parallelism. And myself from Intel and Dana Groff from Microsoft will go through an overview of parallelism in the industry, how it impacts hardware and your use of hardware and software as well. Going to the next slide here, the Manycore Shift. A couple of interesting quotes here from Intel and Microsoft. Back in 2007, our CTO, Justin Ratner, observed that processors were moving from being just single-core processors in the high-volume industry to dual-core and quad-core as well, and easily hitting, at the time he predicted, the 80-core mark within the next 10 years. But the point here being not whether or not we're at 80 cores or not, but we have seen a rapid doubling of the cores per processor over time. And mapping to that is Herb's quote from Microsoft, which essentially says that given these trends of the hardware platform, what you can do as a software developer and when you should do it to best take advantage of the parallelism within the hardware. And that involves identifying which places in your application could best benefit from concurrency, the concurrency that's available from the hardware. Today's agenda, we'll talk about the parallel programming considerations. Why do software developers think that now is the right time to start investing in parallelizing their software applications, even more than they have been before if they've already started? Then we'll talk to Microsoft and what Microsoft is doing, and Dana will touch upon some of the very interesting things coming up. And then we'll talk about Intel Parallel Studio, which is a software product suite as a solution to many developing challenges and opportunities as well in parallelism. And we'll talk about this product offering from the perspective of a workflow that we've learned about over the years when programming parallel applications. This is the industry as we see it, and as you see in this chart, approaching 100% of all processors are becoming parallel processors. We call it multi-core in this case. You see the share back in 2006 and how, as time has progressed, we're in 2009 right now, and about 90% of the processors, whether they be in the desktop, your laptop, or in a server, are at multi-core. They have two cores, at least two cores in the processor. And by 2010, we're expecting that the market in general, every machine that you use, or at least every machine that's shipping, is going to be a multi-core processor-based machine. So now you have parallelism within the hardware. And what does that mean? Here we see that the fact that all processors are going to be multi-core processors requires that as you design your software, you think about scalability today. And the need for your application to scale as more and more processors are introduced, or more and more processor cores are introduced in the hardware. As you see in this graph here, on the x-axis you see the number of cores, and on the y-axis you see the potential performance scaling. So if you have 8 cores on the hardware, then your theoretical limit of scalability is 8x. If your application is fully parallelized. And so this graph here shows you, this chart here shows you areas where you're most likely to benefit the most as a result of making your application scalable, using tools that help you easily do that. Theoretically, if your limit is at 8x on an 8-core processor-based platform, then if you're say within above 7, then 7x scaling of your application, then that's a good thing. It's an excellent thing. But the higher you are, the better you have your application designed for scalability, the more easily your application will adapt to the increasing number of cores in platforms over time. In order to help you do this, to make your application scalable, we have introduced software tools that fit into a development lifecycle to best harness parallelism. And we learned about this based on our interaction with customers who have been parallelizing applications over many years. The first phase when you parallelize your application is the design phase. So here is where you want to use a tool to determine what's your highest ROI. Where in your application are you best off spending time in order to get the most scalability or parallelism at the lowest cost. So really a tool that allows you to assess where to spend your time and effort parallelizing your application. And for this particular design phase, we currently have a tool, which we'll talk about later, called Intel Parallel Advisor Lite on our whatif.intel.com website, and more details later on. The second phase is the code and debug phase. And here we talk about tools that help you develop, create applications, and libraries that help you introduce parallelism. For Parallel Studio, in Parallel Studio, there's an offering called Intel Parallel Composer, and Microsoft has some very interesting capabilities as well that Dana will talk about later on. But really the code and debug phase focusing on compilers, libraries, and debuggers. The third phase is the verify phase. Once you've added parallelism, built your application to take advantage of parallelism, how do you ensure you've done this in a way that addresses the non-deterministic nature of parallelism? Adding parallelism will introduce the notion of errors that are specific to parallelism, such as data races and deadlocks. And the best way to go about adding parallelism is to find these errors, whether it be the threading errors that I mentioned before, or memory-related errors, to find these errors during the development cycle before you actually go into the QA phase. And with Intel Parallel Inspector, you can actually verify during development, understand where you're likely to run into errors that have been introduced into your application when you add parallelism, or even errors that are memory errors that may exist in your serial application. And then finally, once you've verified that you've done what you needed to do in order to lower the chances of your finding errors associated with threading and memory access. The last phase is tuning. So how do you get as close to that theoretical limit of scalability as you can, and what tools will help you identify the opportunities or the reasons why you may be falling short of the theoretical limit of parallelism that you can get on multi-core hardware-based platforms. And for this, we have the Parallel Amplifier, which is in Parallel Studio, and also some other tools that Dana will talk about later from Microsoft, which are upcoming. So creating parallel C++ applications for Windows, Microsoft Visual Studio and Intel Parallel Studio together give you a very, very good solution to do this. Parallel Studio is a plugin into Microsoft Visual Studio, and we'll talk about some of the system requirements in the next slide, but you need Visual Studio on your system in order to use Parallel Studio. It's an end-to-end product suite for parallelism. Together, they address that entire workflow that we talked about earlier. And the goal is to help you create applications that scale on multi-core and many-core processors. And the idea here is for you to be able to add parallelism today, and then as more and more platforms come out that have more and more processors and cores, have you as a developer not need to do any additional work and allow the application itself, having used these tools from Microsoft and Intel, scale automatically to benefit from that hardware level parallelism. Here we look at some of the quick system requirements for Parallel Studio. Visual Studio is required, the standard, professional, and team system editions. Visual Studio 2005, 2008 today, and 2010 when it releases. For operating systems, Vista, XP, Server 2003 and Server 2008, and of course plans for Windows 7 and 2008 R2. For processors, when you use Intel and Microsoft tools, the processors that they work with are Intel and Intel compatible processors. Support for the Intel C++ compiler and the Microsoft Visual C++ compiler as well. Broad use of compilers on Windows is supported. And for parallel programming APIs, the currently released parallel programming APIs, such as threading building blocks, OpenMP, including OpenMP 3.0 support, and Windows threads as well. So we're committed to providing you the tools that allow you to successfully harness the power of many core processors. How do we make development as simple as possible for you and painless as possible for you through these tools? And this is just a snapshot of the tools that are available. Intel Parallel Studio. Within Intel Parallel Studio, we demonstrated the workflow, and within there, Intel Parallel Composer, which has the C++ compiler, threading building blocks, and IPP, which are two libraries for parallelism, and OpenMP, which is an industry standard that the compiler supports, and debugger extensions as well. And then Intel Parallel Inspector to find memory errors and threading-related errors. And finally, Intel Parallel Amplifier it's a profiler that allows you to find the opportunities to help get the most performance, serial and parallel performance out of your application. And then on Microsoft Visual Studio 2010, which Dana will talk about coming up, the Parallel Program Analyzer and Team System, the debugger for parallel tasks and stacks Windows, C++ libraries for concurrency, the Parallel Pattern Library and Agents Library, which Dana will touch upon, and Concurrency Runtime. It's an innovative platform for compositional concurrency. Intel and Microsoft are really accelerating innovation in the industry through the utilization of Microsoft's concurrency runtime. In the future, the software development products that we mentioned, such as the threading building blocks, OpenMP, and Parallel Studio, will use Microsoft's concurrency runtime as a common resource management and scheduling infrastructure on the Windows platform. And with that, I'll hand it off to Dana to talk about the concurrency runtime.
Thank you. Thank you very much, Ivan. So as he let up here, we are releasing the Concurrency Runtime in Visual Studio 2010. You can get that today in Beta 1 form. It provides really three, the runtime itself provides three specific pieces that allow vendors such as Intel to really build great infrastructure on the Windows platform, an infrastructure that composes together. Specifically, it provides a dynamic resource manager, and I'm going to go into that in some detail, but this allows all those different components that are asking for processor resources to work together, and it's going to be a common point for this resource management, and it allows, you to basically extend your programming model, like Intel TBB, in a way that works with all vendors who are providing parallel infrastructures such as the Microsoft PPL or OpenMP in a way that all of these work together. And we also have load balancing schedulers, which, excuse me, there it goes, which allow you to be able to define in your application specific kind of task scheduling. These are, particular policies that you want that particular part of your program to adhere to. For instance, you might have a particular algorithm that doesn't scale beyond 4 cores or 8 cores, and so why try to get more than that? And so you can specify that. And the schedulers and the resource manager are actually communicating back and forth and communicating statistics, how quickly tasks are completing, how many are actually queued up to be run. And so there's hill account climbing algorithms that allow the resource manager to provide more hardware threads to a particular scheduler and to allow it to dynamically respond to that type of work. And we're going to get into that in more detail, as well as this cooperative user mode blocking here. And so today when you do work and you have blocking operations such as I/O, this is all handled pretty much by the operating system, and there can be no coordination in user mode. And in concert, we provide mechanisms to coordinate blocking operations together. And with Windows 7, we then extend that into the kernel, and I'll talk to that. Now, to get a picture about how all these layer together, based on the basic Windows operating system threads is the resource manager, which we call part of the Microsoft Concurrency Runtime. Layered on top of that are task schedulers. Now, there's task schedulers provided by Intel, there's task schedulers provided by Microsoft, and how that layering works exactly, we'll see once those products are released. But you could, any vendor could write directly to the resource manager layer, or they could layer on top of the task scheduler. And then there is the libraries that the application programmers like yourself will be using. And the question here really is what best matches your programming environment. What particular programming model do you want to adapt to? And Intel has OpenMP and TBB, threading building blocks. Microsoft provides the parallel patterned library and an agents library. And I'll show you some examples of what we call PPL. I won't be able to get into agents too heavily, but each of these is a kind of a programming model, a model in our case that is heavily C++, leveraging some of the new C++ OX standards such as lambdas, and allowing you to really express the problem that you're trying to solve in a way that easily can be made parallel. And that's the idea here. The idea is to really enhance the programmer's productivity by allowing them to focus on what they do best, which is solve their business problem and let the runtime, let the C runtime, let the operating system handle really the details of parallelism. That doesn't say it makes it easy. You still have to be a pretty good programmer, and you're going to need some pretty good tools to help you perform and scale. But we want you to be able to focus on what you do best and to naturally kind of fall into successful patterns that can work well with parallelism. So, you know, when you talk about your application, it's usually not simply one, you know, main and a couple of, you know, methods out there. You're probably incorporating libraries that you wrote, libraries that were written many years ago. You may be writing, you may be having code that you purchase from other vendors, and those vendors may be layering on top of, let's say, Microsoft PPL, or maybe they're using OpenMP, or maybe they're using TBB. You want all these to work well together. You don't want to run into a situation where you have a billion thread pools out there and all of them think they own the whole machine. Yes, we may have 80 cores. We don't have that today. And if everyone tried to get 80 cores or 4 cores, and you're on a 4-core box, and they're scheduling things, you'll find that there's cache pressures, there's basically resource demands that don't allow your application to scale well. And these are things that really are outside of your control as a programmer. You want to be able to have these disparate pieces compose well together. To do that, they need to basically standardize on a single resource manager that understands the hardware architecture and abstracts that to the program, and then manages scheduling that hardware to the application in a way that allows the application to run well. Now, I talked about dynamic resource management, and I'm going to try to give you a pictorial example of what that really means. So, for instance, consider a 4-core machine, and you know, we talk about cores in the sense of what the operating system tells us is basically a physical hardware thread, and in the case of the concurrency runtime, we're aware of you know, potential cores that are on the same chip, and we pay attention to the kind of distance between chips. And so these are all part of our algorithms, stuff that we as the runtime provider find is important and we should do well, and areas where you as an application writer who have a particular domain knowledge, that's not something we expect you to have to write. And so let's provide that for you. So in this case, we have 4 cores. I take the default scheduler policy and I create an application and it has a scheduler. And so it's going to get the minimum of 1. I'm going to have at least 1 core and a maximum of the maximum number of those cores. And these are, I'm going to potentially run all my tasks on all those cores. Now, I happen to call a method that actually starts yet another scheduler. And it, too, takes the default, which is going to be 1 and 4. And so instead of trying to spread everything over all 4 cores, the resource manager says, well, why don't you two play nicely together and each of you have half the machine? So 2 on one side and 2 on the other side. Now your application has these 2 sets of active schedulers working and actually sharing work and hopefully you know, proper affinity at that point in time. Now, what happens if I run out of work? So in my first case, the scheduler 1, it runs out of work on one of those cores, and that becomes idle. The resource manager detects this and then assigns you know, some specific threads to scheduler 2 to be used on that 3rd core here. And so it steals some work from, in this case, core 4 and moves that over to core 3. So now we are, again, keeping all of your hardware resources used 100%, because they're there. You might as well use them. Don't just have them just sit idle, and get your work done faster as a result. Now, let's say you have a higher priority scheduler come in, some high priority work that maybe it's doing some audio processing, maybe it's doing some UI stuff that you really can't afford to be interrupted by other things, and it really needs a minimum of 2 cores for it to scale. So you specify this as a high priority scheduler. The resource manager recognizes that and says, okay, well, I've got a batch of schedulers out there, I've got a lot of work going on here, but I'll give you your minimum of 2, and I'm literally going to take that away from those other schedulers. And so they get less hardware resources to kind of make way for this high priority scheduler. Now, that works really, really well on platforms going back to XP. You know, Vista, those are fine. Windows 7, most of you, I hope, have seen the release candidate of that. Download that today and try it out. It's great. And, you know, Vista did a lot to really help scale the platform. And Windows 7 takes that even further. You've got, in the x64 edition, something called user mode scheduled threads. This is kind of exciting because, you know, the concurrency runtime understands when you try to do an event or you have a lock, when you're using particular concert constructs to do those events or to do those locks. When you're doing kind of traditional Win32 APIs to do events, to do locks, to do I/O.
Excuse me for 1 second. I think you might have dropped off the webinar.
Really?
Yeah.
Okay.
I don't logged in as a panelist anymore.
Okay, I will try to log in again. I'm sorry. It looks like it works here.
Yeah, we could still hear you, but it doesn't. You're no longer a panelist for some reason.
So I will close the window that says I am, and
you're back again. Let me switch you over to presenter.
Okay, there we go.
Be good now. Thank you.
Thank you. So you didn't get to see my animations here.
No, we did not.
so here's the animations again. Sorry about that. I could see them on my screen. And so the animations here where we shared, they stole some tasks as I was talking, and here's a high priority scheduler. And now we're talking about Windows 7. I apologize for the technical difficulties there. So, you know, the concurrency runtime runs back to XP. You know, so you can, you know, you can go into XP, you can write Vista, and you can just write to that, and that just works, and that's great, right? As new features of the OS come online, such as under Windows 7, under the 64-bit edition, Concert knows about that. It says, you know, I've got this available. I've got these user mode scheduled threads. And it will use those, unless you've explicitly said don't, to now extend the cooperative blocking concept to operating system blocking events. And so you can write your application as normal, run it as normal, and then it just starts using this new feature and behaves better, basically, as a result of that. I'm going to get into a minute what UMS threads are, but you know, I wanted to point out that this new feature on x64, there's really no API restrictions, and from your point of view, there's really no changes other than the fact that it works really well if you're writing to the concurrency runtime. So let's take a look at what that looks like. So you define work as tasks. That's the term that we use for Visual Studio 2010's concurrency runtime. So you have this piece of work that you're a task, and you're going to run it on a particular user mode environment. And this, we call this task that we're going to then schedule. And so we schedule that task, and we start executing that task, and it makes a Win32 call. So that's calling into the kernel. And that kernel mode operation continues on, and it then gets blocked by something. So maybe it's doing an event, maybe it's doing some I/O. Whatever it's doing, that blocked operation causes the UMS environment to signal to the concurrency runtime in user mode to say, hey, we're blocked. Please schedule something on this core. So that while that operating system work, while that kernel work is blocked, you can continue using that core within your quantum doing user mode work. And so new work is now scheduled on that core without losing any sort of quantum. Now when that, of course, that kernel operation becomes unblocked, then we have to reschedule that task. And so the kernel signals again to the concurrency runtime. By the way, I will say sometimes concert, which is our internal short name for concurrency runtime, and that's what I mean when I do that. But I'll try to use the full name. So so it'll then communicate with concurrency runtime to reschedule this task that had been blocked. And so it'll put that back into its schedulers and run it the next time it has an opportunity. So what's different about this? Well, in today, when you call a 132 API and it's blocked, it stays blocked until the operating system decides, oh, I'm going to reschedule this. And it's going to pick some thread to reschedule onto that core. And it may or may not be in your quantum. So are you going to get more work done? Well, it depends a lot on your application, how many times it's doing these type of calls that it's actually going to be blocked, and if it has other work that it can do. But assuming that it does, this is then going to give you some percentage of improvement in performance. And that's, again, going to be somewhat dependent on how your application is written. But the beauty about this environment is we've now moved control on scheduling of work on the hardware into user mode closest to the application. So you're now able to kind of give the hints to the runtime to say, hey, these are my important things. These are things that I really want to these are the type of work I need to get done earlier. These are the things I want to give more resources to. You have that ability to define that with your schedulers, with the dynamic runtime, and make that work. So let's have an example of some of the code, because that's really what you've got to get down to. Let's take a traditional matrix multiplication. It's usually a nested for loop, fairly straightforward. Well, okay, so I'm going to make it into a parallel program today. Well, I'm actually cheating here, and I'm using the SDL thread, which is a template here to do that. That's the lambda you see on the outer for loop. But I'm saying, hey, let's create a batch of threads, and this is kind of hard to look at, really hard to maintain, and there's a whole bunch of stuff here that has nothing to do with multiplying it. We've got static partitioning. Now that works out well for this particular problem, but if I have an unbalanced set of work inside that for loop, it's not all that great. I actually have to pay attention to synchronizing each of my threads. So I'm going to have to create a whole bunch of events, and I've actually written this, and the reason why I'm counting down is that every once in a while, if I count up, I make the wrong numbers, and it's error prone. So you got to be careful there. And of course, for people who've debugged multi-threaded applications, you can and tried to test multi-threaded applications, you really want to try to reduce the number of times you have to actually try to find these type of bugs in the kind of the surface area of having these type of bugs. There's a lot of things that I'm going to do over and over and over again when I'm doing multi-threading, and personally, what I do is create wrappers for that. And then, I talked about my interlock decrement there and why I use that instead of an increment. That's kind of a trick to count down, reduces the number of times I have errors. But I'm not reusing those threads at the end, right? So I'm just going to throw them away. So what happens, you start building thread pools and things along those lines. You've got some synchronization. Now, what do I do if I did this in PPL? I don't want to do this, right? If I did it in PPL, I would simply turn that outer for loop into a parallel for loop. Now I'm using some new syntax here for C++ OX with the lambda, but all I'm doing here is taking that parallel for loops and just on the outside making it a parallel for. And by the way, you can do this in TBB. Looks a little bit differently, and Shobhan's going to show you that. We're all kind of converging onto syntax like this, and so I think it's going to become this simple going forward. And this is the type of thing where you're saying, hey, I'm going to focus on my problem, which is this math multiplication. And I don't have to worry about, do I need a thread pool and how do I synchronize this? I just say, look, I want to do this for loop in parallel. Now, what is it going to look like when I debug? So in Visual Studio 2010, Beta 1, you download it now, you have two new windows. The Parallel Stacks window, which is really providing you a hierarchical view. You can view it up or view it down, whichever way you think is the correct direction, at how the tasks are particularly called, how they've been laid out, That sometimes is great for kind of mapping out all of these threads that are working, and you can filter it down to a small number, and then you can kind of hone into what you're trying to debug there. You can see tasks as well as threads. Both windows have been enhanced. The task is a new window, so threads is going to be pretty much a superset. But what's nice in the parallel tasks is you're going to be able to see if something's waiting, if it's running, if it's been scheduled. So these would be threads that aren't running, right? So if you think about it in a threads perspective, you only see the threads that you've already scheduled and you've got going and things along those lines. But if you have a whole batch of tasks that have been queued up, instead of waiting for them to be started out of a particular thread pool, you're going to actually see these here that they've been scheduled for later execution. We also, in this particular case, have an example where we're showing deadlocks that we're able to actually, in some cases, detect a deadlock, and we'll show it when we see that. We also have in Team System a parallel profiler. I could spend an hour talking about that, but just to give you a very high overview, you can actually see utilization here. So the green is your application. The kind of orange there is the system as it interrupts and tries to get some resources. So you're going to be able to see what the system contention is on the CPU utilization screen. One of the areas that I find really exciting are both the thread blocking and the core execution, because this actually shows in this kind of swim lane way my threads or my cores, and I can start seeing things ping pong between the cores, or I can detect what one thread is waiting on, and then there's even some areas where I can instrument my code and highlight that more in the thread blocking view, so I can see where I have particular parallel, let's say I have a parallel 4 operating. I can see when I've got an event that has then been satisfied and releases another thread and things along those lines. So this is kind of a nice way for me to visually look at my application, see what's going on, see where my resources are being used, and see potentially where I might have some problems. And there's common problems like this stair-step design that you see in the CPU utilization there that usually indicate that I've got some sort of synchronization problems. And with that, I'm going to hand it back to Shoban to talk about the composer.
Okay, thank you, Dana. Now we'll talk a little bit more about some of the specific tools that you can find within Intel Parallel Studio. When we talk about Intel Parallel Composer, we talk about our compiler and libraries. This is a little screenshot of Visual Studio, and you can see that you can actually find the Intel Parallel Composer. Once you install Parallel Studio on your system, you can just go to the project screen, find Intel Parallel Composer there. It'll automatically show up, and choose either the Intel C++ compiler or the Visual C++ compiler for compiling. And since they're source and object compatible, you can have some modules of your application compiled using the Visual C++ compiler, and some modules compiled using the Intel C++ compiler. It could kind of mix and match, really, Intel and Microsoft working together to make sure that we give you the best solution as a developer to build your application. The key message here, though, is that once you install Parallel Studio, you can get access to the Intel C++ compiler directly from Visual Studio. This is that parallel matrix multiplication example that Dana talked about earlier, and this is, when you use TVB, this is how the code looks today. You see about 4 lines of code, but the good news is, now this is of course a lot less code than what you saw in the first example that Dana talked about, but the good news is that you see this example. And remember, we introduced the threading building blocks as a solution to abstract native thread-based parallelism about 3 or 4 years ago. So we've had this out in the marketplace for a couple of years, been experimenting with it and making the amount of code that you have to add to successfully use TVB less and less over time. And with the introduction of Visual Studio 2010, we'll have a solution with TVB that allows you to add just that one line of code to introduce parallelism to your application, scalable parallelism. And then you think about what is it in each of these libraries that you can use, that you can benefit from, that will allow you to get the best functionality and add parallelism to as many parts of your application, whether it's algorithms such as the Parallel 4 that we're talking about here, data structures such as concurrent queues or hash maps, whether it's mallocs, which we have in the threading building blocks, scalable mallocs, anything that the next best step to determine which API to use is just to kind of take a look at the components of it and see what maps best to your particular application development needs. And again, the compatibility is something that we're focused on. Dana talked about it earlier. All of this is designed to work together, so you get to make the choice of what works best for you. Now, in the composer area, designing, building, building and coding and debugging, the compiler and an example of the library that we showed earlier, the threading building blocks. Then when you get into the verification stage, Intel Parallel Inspector, which is a tool that runs on your binary to help detect errors before they actually occur. So here we take Parallel Inspector and we run it on this application. And on the left-hand side, you see that we've run this. We have about 6 or 7 different test results. So we've had 6 or 7 different applications, or maybe the same application using different data sets. Different results. So as you make changes to your code or try different things, you can see what the differences are by looking at the different results files. In the result file, you see here in the center where Intel Parallel Inspector within Parallel Studio was able to find a bunch of memory errors. So here we're using the memory error detection capability within Parallel Inspector. Remember, it also has a threading error detection capability. So if you run the threading error detector in here, then instead of seeing these invalid memory accesses or uninitialized memory accesses or memory leaks, you'd see things like data races or deadlocks. And what it does is actually instruments your code to check when memory is being accessed and how it's being accessed, to give you a warning ahead of time of things that you want to probably fix before you think that all of your development work is completed on this application. So here you see the integration within Visual Studio. A nice, simple toolbar, easy to choose what kind of error detection you want to proceed with on the application. You see the memory errors listed, and on the right-hand side you can edit what you've fixed and what you've not fixed, really keep status of what you've done and what you haven't done. And at the bottom, you can actually drill down to the source code. So here, if I take that allocation site in this C++ file, line 44, if I double-click on that, that'll take me to the source code, and I can actually edit that source code, make any changes that I need to address this information. This would map to the invalid memory access further up there, and make fixes to ensure that I choose and find these errors, potential errors in the application before they actually make themselves evident when the application is running in production. So this is the error detector, verify with Intel Parallel Inspector. And then the tuning phase, we have Intel Parallel Amplifier. Here is an example at the top of the drill down into source code. We can do a hotspot analysis, so you can find when a particular function is running, how much time it takes and how much time that's contributing to your running application. You can do a concurrency analysis or a locks and waits analysis as well, and also compare results. At the top here, you see an example of the concurrency analysis, where what this says is that when color is doing this calculate pixel, during that time, the 1.652 seconds, 625 seconds that it takes, about 75% of that time we have poor concurrency. So it's found that the hardware machine that you have may have 2 or 4 cores where the amount of concurrency at that point in time is actually less than that. So you have an opportunity here to parallelize this, to get more parallelism and more scalability to make as much of this runtime ideal as possible using the Intel Parallel Amplifier tool within Intel Parallel Studio. And this is a more detailed view of concurrency analysis, where you see, as we mentioned before, green is ideal and red is poor. The length of the bar is time, and the color is the utilization while the function is running. This is the screen before the drill down to source code. You can see the average CPU utilization, and that most of the time here, the app is using only one core, which you see on the right-hand side. 1 is poor, 2 is good, 2 is ideal, which means that it's detected 2 cores, and it wants you to have 2 active threads running as much as possible to take advantage of the scalability that's available to you. Red is underutilized, green is good. So really getting you insight into your application and finding out where in your application you're not using as much parallelism as the machine will afford you. So we talked about the compose phase, introducing parallelism, finding errors with Intel Parallel Inspector, tuning with Intel Parallel Amplifier, and on the whatif.intel.com site, a prototype technology that we have, Intel Parallel Advisor Lite, that allows you to prototype parallelism on a serial application. What you do is you annotate your code, and you see, given the recommendations that you get for highest ROI, where to spend your time parallelizing. Given those recommendations, if you prototyped with that recommendation, say use the threading building blocks, for example, how much parallelism are you likely to get in your serial application? So this kind of gives you a snapshot while you're designing your application into how do you make sure that you're designing parallelism in the right way to get the most parallelism before you actually do the work to add the parallelism in, really kind of prototyping to do that. And Parallel Advisor Lite, when you get it from whatif.intel.com, requires that you already have Parallel Studio installed on your system. This is an example of Parallel Studio and a customer success and benefit. NVIDIA gave us a testimonial when we launched Parallel Studio at the end of last month. And here on the left-hand side, you see NVIDIA using Parallel Inspector and the errors that they found, memory errors in this case. They used Parallel Inspector that they found before when they first ran Parallel Inspector on their code, and then they made these fixes. And at the bottom, you see that most of these fixes have been made. And the before and after really hit home with NVIDIA, where they acknowledged that it made their development faster and more efficient, using all of the tools within Parallel Studio, within Visual Studio, really shortening the overall development time and speeding up the software product's time to market. Really, how do we make you more productive developing parallel applications and offering you the right tools to help you get there? So really, Intel and Microsoft working together as your partners in parallel computing. The Parallel Studio on the left-hand side, which is integrated into Visual Studio, that you purchase separately and that you can use within Visual Studio, and a lot of the cool new technology coming up in Visual Studio 2010 that Dana talked about. For more information, 2 great websites, intel.com/go/parallel to find out more about Intel tools that we talked about earlier, and msdn.com/concurrency for the Microsoft tools. And you can learn more by trying out Parallel Studio from the Intel site and the Visual Studio 2010 Beta 1 from the MSDN site.
Okay, we're going to open up the floor right now for questions. And hold on one second. Dana and Shoban, I'm going to unmute both of you so you both can answer them freely depending on who has the question. We have one question. I think this might be for Shoban. Is the memory and thread checkers dependent on using the Intel compiler or okay with the MS compiler?
The thread and memory checker, Intel Parallel Inspector, can be used with applications that are built using either the Microsoft Windows compiler or the Intel compiler.
Okay. Next one. When the Visual Studio 2010 will be formally released, when will it be released?
Well, the date hasn't been set. The exact date hasn't been set. Obviously, it's going to be in 2010. We have Beta 1 out now. We're looking at a Beta 2 later this year, and I would venture to say that sometime in the fall. And you know, we're going to have a release candidate and an RTM after that. Microsoft generally doesn't release dates too far in the future anymore. So we can say it's in 2010, and I'm, you know, hopefully optimistic that it'll be not at the end of 2010, but sometime earlier than that.
Okay. Next question. Does this only work for Intel processors? How about AMD? I'm not.
Well, the answer is yes. Both processors.
It works for both. Okay.
All the
next
tools that
question.
you saw today. Yep.
Okay. From Herman, with the embedded application, is the C++ compiler still work for other non-Intel processors such as Freescale processor?
We do have a C++ compiler for embedded OSs, but I don't know. I currently don't have any more information beyond that. In general, you know, we've had this question come up several times, and it's important to point out that at Intel, what we try to do is try to offer a suite of tools that allow you to write applications that are the best performing applications on that platform, whether it be an Intel platform or other platform, on the OS that we support. You know, and have those tools be the best tools that you'd use, you know, compared to other alternatives that you may have. So we strive to help you develop applications that are best performing applications on any platform.
Okay. Must Intel concurrency analysis run on target HW, I'm assuming hardware, or can it run accurately on a developer workstation that is different than the target?
Let's see, that's concurrency analysis. Okay, so I assume you're talking about the concurrency analysis feature within Intel Parallel Amplifier. It will work accurately on the developer workstation. The thing is, though, when you look at concurrency analysis, the current form of the tool will give you information based on its detection of the number of cores on the development platform. So if you have a certain amount of concurrency on and for your application running on, say, a 4-core platform, you can expect that you'll have the same level of concurrency on a 4-core platform that is not the actual development platform. However, if the concurrency is different on that different platform, how the application will behave on that target platform with a different concurrency level. You won't get the specific information, but you'll at least know, based on your investigation into the development platform, that there is where the opportunities are for scalability, and you'll know what in your application is contributing to your not getting the optimal scalability. And the changes that you make, especially if you design it using tools that we talked about earlier today to make your application scalable and future-proof, the changes that you make are likely to have benefits on the target platforms as well, which are not your development platforms.
Let me jump in here a bit, Siobhan. One of the other things that comes out here is depending upon the tools you use. So if you're coding threads and you're specifically looking up the number of cores, you're not going to scale as well if you're making the assumption or you've hard-coded the cores to 4 or 8 or something along those lines. But with either Microsoft's Concurrency Runtime or the Intel TBB, you can sit there and run with the concurrency that's best for the hardware that the runtime detects. That doesn't solve all your problems because you might have cache pressures and might be dependent on cache sizes. But one of the things that I've found is that some people who are using other libraries out there, they often hard code their concurrency, or they have to actually write their algorithms with some assumptions about the number of processors they have. and that has scalability concerns.
Good point.
Okay, next question, will VS 2010 compiler support OpenMP 3.0?
So I think what they're asking is, does Microsoft's OpenMP offering in the Visual Studio 2010 conform to the 3.0 specification? The answer is no. We have done some bug fixes on our existing OpenMP implementation, but we have not extended it. The 3.0, the Intel has a 3.0 implementation. I think that's available today in Parallel Studio, right, Siobhan?
Yeah, that's correct. Yep.
Okay, next question. Explain positioning between the VTune product and Parallel Studio.
That's a good question. I would say the best way to position it is VTune and whatever the future product will be has a lot more, has some additional features which have been found as useful to those developers who are in the high-performance computing area, who are looking to get architecture-level detail to get the most performance possible. That's how I would characterize VTune. And Parallel Amplifier, which is in Parallel Studio, is a great tool built into Visual Studio. VTune, of course, doesn't require Visual Studio, but Amplifier does. And that's a great tool to get you started on the track to parallelism, to understand at a high level quickly where your performance opportunities are, whether they be in your serial application or in your parallel application. So those are, I think, the two benefits. I think the way to think about it is there will be additional functionality in VTune, and if that functionality at that depth and granularity is important to you, then that's the offering that you should focus on. But if Parallel Amplifier, suits your needs and is available on the within your development environment, then that's the right one for you.
Okay. How about managed code integration?
Now, I can speak to the Visual Studio 2010. Of course, the PPA and the debugger windows work well with our managed code and what we call the parallel extensions and the parallel link product libraries that are in C# and the .NET framework. So .NET Framework 4 has a number of parallel enhancements to it, and the tools in Visual Studio that I showed in 2010 work equally well in native as well as managed code.
Parallel Studio currently supports just C and C++ code, and that's the focus that we chose, given feedback from many of the customers and developers we talked to, and current needs to get started parallel programming. But we're investigating additional language support. But as of today, just C and C++ with Parallel Studio.
Okay, next question. Can someone talk more about the decision to use one compiler or another on a particular module?
I can, quickly touch upon that. We had, one of the customer successes that we've had at Intel using the Intel compiler is Oracle. And when they decided to use the Intel compiler, they didn't want to, have to recompile all their code using the Intel compiler. So what they did was they found some performance-sensitive modules, which they were getting specific benefit from when using the Intel compiler. So what they did was they took those modules and they compiled those with the Intel compiler and left the rest of their code compiled using the Microsoft compiler. And since they're source and object compatible, they'll link together. And Oracle was able to get the performance benefit afforded by the Intel compiler, and thanks to compatibility with the Microsoft Visual C++ compiler, not have to do a complete overhaul of their application. And that was just one example of where those both were used in conjunction.
Okay, next question. Is parallel profiling for VS 2010 available for versions other than Team System?
The decisions on that haven't been totally finalized, but as of today, the parallel analyzer is bundled with Team System.
Okay, next question. Does the Parallel Composer help out with any GPU computing, such as NVIDIA Tesla processing system, or is it primarily suited for the CPU computing?
The Intel C++ compiler is available on Windows, Linux, and Mac operating systems. And right now, the processors that are in the platforms that run on those, and they're primarily CPUs right now. That's where the Intel C++ compiler focuses on its optimizations.
Okay, next question. You mentioned with UMS some tasks can be rescheduled after they were blocking, but could this also not stall that task if it gets rescheduled a few times?
Well, remember what we're dealing with here. You've blocked, right? And so you're not going to be having any forward activity on that particular task because it's blocked in the OS. Let's say an I/O. Now, I/O is a pretty long operation. So by the time it is rescheduled in that, we're hoping that that blocking activity has been met. And again, as an application writer, you have some control here because you can group these particular tasks together under a particular scheduler. And so how deep your scheduler queues get is really the question you're asking here. And write your application so you don't have deep scheduler queues, and you won't have any problems there. Although, if you've got problems to that extent, I'm going to probably point out that you're going to then see it in different ways, in that now you have multiple schedulers who are all trying to get access to that particular hardware needs. And maybe what you're really saying is that you have an application that needs a lot of cores. Today, I don't see a lot of applications like that, and I'd like to. So that ones that do much, much better on lots of cores, because that's where we're going, right? And we're not going to be getting a free lunch anymore by having by writing applications. It just gets faster because the CPU gets faster. The only way we're going to be able to write more complex applications is to be able to scale as the CPUs get larger.
Okay. Do both tools work well within Virtual PC or VirtualBox?
Visual Studio 2010 does. I mean, in fact, we do a lot of our testing within virtual PCs.
Okay, next question. Can we use the latest Intel C++ compiler with Intel Parallel Composer? How can we distinguish them?
With Parallel, so when we launched Parallel Composer, we introduced the latest C++ compiler that was available to us at that time. And as we release new C++ compilers, we'll find the right timing to introduce that compiler within the Composer offering. But to more specifically answer the question, it is a version 11-based compiler, and we will offer updates, the one in Parallel Composer, and we will offer updates to that compiler that introduce new technologies and new updates.
Okay, next question. Does the concurrency runtime work on Windows XP?
Yes, that's actually very simple. And that's actually one of the advantages with coding to the concurrency runtime is you write code once and it's going to be able to run just as well on Windows 7 as it is on Windows XP.
Okay, the example code shows a matrix multiply routine. However, how small can the size of a matrix be? I mean, this is most likely working on a huge matrix. How big is the overhead of threading using Intel TBB or the Microsoft solution?
So you're asking really, how big is that? How big or how small? Maybe the real question is how small can that inner loop be, and still get some level of scaling. And this is a valid question and one that you have to think about. We really are trying to make the overhead of the runtime as small as possible. And what we're finding, I don't have exact numbers but tens of microseconds type of thing. You really are able to scale with very, very small units of work. Now that doesn't mean I'm going to want to encourage you to do a parallel for over an addition operation. That's a little too small, and now you're going to have the overhead of all these threads that are going to overwhelm the performance gain you could have seen by scaling out. And so, that's what you have to think about. This is where you as a programmer add value, and that is say, well, how can I decompose my tasks to be fairly small, but not too small, but fairly small logical units that I can run in parallel. And this, with the tools that both Intel and Microsoft are providing, are going to be able to show you, did you get it right, and is your application scaling well? I can't speak to the TBB overhead because I honestly don't know, but I can say that from the Microsoft side, we're always driving that overhead smaller and smaller and smaller. And how you write your code, whether you're using a parallel for or you're using maybe more coarser and heavier weight operations, really dictates the size of those tasks. And this is part of going deep into it, and maybe we can come back sometime and we can have a fairly deep discussion about the designs choices you have to make over the particular programming models.
Okay, does Parallel Studio integrate with the current VS 2010 Beta 1?
Siobhan, you're going to have to take that one.
Yeah, no. We do have it working with 2005 and 2008, and we do have a plan to have it work with 2010, though I don't know what the status is with Visual Studio 2010 Beta 1.
Oh, okay. Next question. Will Intel Larrabee also be supported, or does it have its own API for threading?
I'm sorry, could you repeat the question?
Sure. Will Intel Larrabee also be supported, or does it have its own API for threading?
Today's presentation, we're talking specifically about Parallel Studio, and currently we haven't announced anything for Larrabee, so I don't have an answer to that.
Okay. Second to last question. So when will we need MPI with these types of tools to schedule across cores on separate machines transparently?
And adds evil grin. Oh, well. But so these tools are talking about cores in the same machine, and we're not addressing MPI in this particular talk. There is some enhancements done to Visual Studio 2010 to support compute clusters and high-performance computing. There may be some Intel offerings as well in that space, but that's outside of the concept of this discussion.
Okay. Can someone explain the positioning between the new Intel CT framework versus Parallel Studio, TBB?
I don't have that information handy. Sorry.
Okay.
Today we talked about Parallel Studio, which supports TBB, and we have talked about the CT technology, but I don't have a specific comparison handy, other than to say that both solutions are really APIs that are meant to help developers take advantage of parallelism, with CT having more of a data parallel focus through some of the unique, through the way it actually, or through some of the APIs that it actually makes available to developers to get performance.
Okay, and our last question, actually I misspoke because someone just wrote in another question. Do we need both Intel Parallel Studio and Visual Studio to complete a multiple threading task on a multiple core processor?
Yes.
Well, I mean, it depends on how easy you want it to be, right? So if you're writing just to Visual Studio and you're running your own threads, for that matter, you could just use other tools and not even have an IDE. The advantage here is with Visual Studio, with the Intel Parallel Studio, is the ease and the enhanced productivity you're going to achieve when you add these different tools into your development environment. And it's not, can I do it? Yeah, well, if you're capable of doing it, sure you can do it. But can you do it well? Can you do it quickly? Can you do it so that you actually can focus on your business problem and not on writing parallel code and parallel infrastructures and parallel frameworks? If you want to let that be done by Intel and Microsoft, then these are great products for you.
Okay, and our last question, does parallel profiling for VS 2010 offer anything not available in Parallel Studio?
I want to say they're complementary. Okay, so you saw the debugging windows that we had. You saw some of the performance analysis work that's done in line with the Parallel Studio. When we're here together, not as competitors, but as partners. And we're providing tools that really do different things. For instance, the PPA, or the Parallel Analyzer from Microsoft, it's leveraging, which is available in Vista and later, to do that analysis. And Intel, when they do their analysis, they're doing it differently. And so they have a different picture. They have a different set of counters and statistics that they analyze and they provide to you. And the question really is, for your application environment, for your development, for your problem set, what are the best tools for you to use? There's a suite of tools here. I personally use different tools for different problems. And I find, both tools that I've written myself or tools that other people have written sometimes even to try to analyze where I've got problems in my code that for scalability. I mean, it's not necessarily easy, and so you want a rich tool set to help you out here. And we can try to make it as easy as we can in the programming model, and then we focus on our tooling. And Intel has their focus, Microsoft has its focus. Together, I think you've got the best of all worlds.
Yeah, and to build on that, you have Intel expertise in the Intel tools and Microsoft expertise in the Microsoft tools. And what we're really trying to do is take that expertise and allow you visibility into the platform itself, and working together with different views and different insight, give you all the information you need to get the most performance that you can get, whether it be the Parallel Performance Analyzer or Parallel Amplifier.
Okay, great. Thanks, Shoban, and thanks, Dana. And thank you, everyone out there, for all the questions. Again, for more information, you can visit our website. We have a special link, www.programmers.com/Intel. And you can also, if you have more questions, send those to team.alm@programmers.com. And once again, everyone, thanks for taking the time out of your day for attending today. And all the information is listed there on the screen if you have any other questions. And once again, thanks, Shoban and Dana, and you guys have a great day.